These are the notes for LT2 in the thermodynamics unit. And in LT2, you need to be able to model and interpret the model, but model the movement of heat in conduction, convection, and radiation. So those are our three primary energy transfer methods. You'll be asked, if you were in class, to Google both the definition and an example of each method of conduction, convection, and radiation. And so as we go through there, hopefully some people found for conduction, we'll just start with this one, that this is the energy transfer, it's all energy transfer, but it occurs by collisions. So it occurs by collisions between molecules and their immediate neighbors. Okay, so it occurs by collisions between molecules, and their immediate, neighbors. Alright, so think about that. Going back to kinetic theory, we know solids, liquids, gases, plasma. And which of those are the molecules closest together where they would have a really tight immediate neighbor? It's kind of like living in town where it's house after house after house. Would that be a solid? Would that be a gas? Kind of get that in your mind. And hopefully you are thinking solid. Okay, so conduction is usually in solids. And the reason for that, there's a lot of direct contact or touching of the molecules. Okay, there's lots of touching, direct contact where that energy can just go between one to the next to the next. Because remember, these things aren't sitting still in a solid. They're vibrating back and forth. And so when they bump into each other, they transfer that energy during that bumping together. The best conductors are metals. Okay, there's a reason that we use metals when we're talking even electrical conduction, because they have lots of free electrons, which is a chemistry thing. We'll talk more about it during the electricity unit. But metals allow the energy to pass through. Think about pots and pans in your house. Okay, the part that sits on the stovetop is metal, right? And there's a reason for that, is it transfers the heat evenly throughout. So when we share our examples, all right, we have pans. Think like metal spoons. You know, if you've got a metal spoon and you leave it in a pot of boiling water, you better not just grab onto it. When people are welding, okay, you're working with metals again. Okay, there's endless examples. So if you wanted more of them, hop on Google, type in examples of conduction. Okay, but direct contact. You go to grab something out of the stove and you're a silly person that doesn't use an oven mitt or something like that. We know not to directly touch something because that would be conduction into our body. So that's the first one. Second one, convection. This is the transfer of energy. So same as the first, we're talking still transfer of energy. And this is usually by currents in fluids. Okay, so we have to remember what fluids are, because this idea of fluids is not just our common everyday thought of it, where you got to stay hydrated, you got to drink water, you got to drink fluids. When we talk fluids, remember it's anything that can flow, so that can be a liquid or a gas. A liquid or a gas. This idea of convection currents. You think back to middle school, you would have had a weather unit, and you would have talked about air currents, and then you would have talked about ocean currents. And hopefully this will look a little bit familiar, where when we talk about currents, it's due to cooler, kind of denser fluids sinking. Okay, so they would sink to the bottom, whether it's the ocean, whether it's cooler air in the atmosphere, sinking towards land. And then your warmer, less dense fluids would rise up. So when you're boiling that water, okay, they come to the top. Those bubbles come to the top. To make room, it kind of pushes the cooler stuff down. Same with ocean, same with wind. You may remember the idea of land breezes and sea breezes. Okay, it all works on this idea of convection currents. So if we think about, and you were to Google some examples, some real good examples that I've heard in the past, a lava lamp. Okay, nothing happens at first. You plug it in, and sure, the light comes on, but it takes a while for that blob of stuff, whatever that mixture is within the globby stuff. As that warms up, those bubbles kind of get bigger, and it rolls to the top. And once it gets to the top, it sits up there a little bit, and it's going to cool down. It's going to come back down. And the heat source is coming from the bottom, like the pedestal of that lava lamp. So that's going to bring it back up. All right, so that would be a convection current. Heaters. Okay, there's a reason I'm not tall, but I know my uncle would always complain when we were in a hunting shack that, my gosh, it's hot in here, he'd say. But he's a lot taller, so like all that heat would rise up like to his face, where I'm, huddled in the corner trying to stay warm while the heat rises up. Think about a hot air balloon. Okay, you've got the burner in there that's heating up air, and when that air heats up, it becomes less dense because it spreads out, and it rises up and catches the material, the fabric of the balloon, and causes it to rise in the air. Okay, our classic, almost boring example is boiling water. But it's the same thing. Air currents, air and ocean currents. Anything where a gas or a liquid is transferring energy. We just bought a convection oven to replace our toaster. So you think about a convection oven, it's going to move hot air around there in order to brown your toaster, your bagel, or warm up your pizza, whatever it is you're using it for. All right, that's the second method. Third method. Radiation. Okay, when I say the radiation, a lot of people automatically go all Hulk on me, all right, and they think that it's that type of radiation, and it could be, but that's a really, really small portion of it, that gamma ray idea. So this is the transfer of energy by electromagnetic waves. Big word. We'll get more into what does the word electromagnetic mean. We'll do that in the electricity and magnetism unit. But right now, just realize that a magnetic field and electric current they self-propagate. The magnetism creates the electric current creates the magnetism, and it's a never-ending series of events there. Hopefully this looks familiar from middle school. You would have seen something called the electromagnetic spectrum. And over here is that Hulk thing. Okay, there's the gamma rays. Super high energy waves. If you've ever gotten hurt or you went to the dentist, you know about X-rays. Okay, not as high energy. And we've probably all had an experience with ultraviolet waves. Maybe we got a sunburn. And then we have visible light, the rainbow. Then we have infrared. IR is infrared waves. And then we have microwaves, which most of us lazy folk use a lot to get stuff done quick. And then radio waves, which are not sound waves. I'm not talking the music that's going into your earbuds. This would be like getting reception to 94.5 or 95.3 or whatever. Or between cell phones. Cell phones run in this range between radio and micro. All right. But this idea of radiation, these waves, they're somewhat invisible. Okay, you can't really, they don't need a medium, they don't need something to travel through. And so these guys kind of look like this coming at you. Sometimes they'll have long wavelengths, sometimes short. But if we could see them, that would be the pattern they take. But if you think about infrared is essentially thermal energy. So if you cook something in the oven, you bake something, I should say, in the oven, that would be an example of radiation. Everything coming from the sun emits every single frequency here, okay, every single type. Anything that creates its own light. So a light bulb, okay, when it's lit, of course, that creates visible light. Okay, there's endless examples of this. So cooking your food, microwaves is radiation. X-rays is technically radiation. I know it doesn't feel like thermal energy, but it's still energy. Okay, so it's a type of energy transfer. Almost wrapping it up here. But it's important to know that this idea of thermal energy, thermal energy only flows, so flows from, I'm going to go blank to blank object. So stop and think here. Okay, thermal energy flows, does it flow from the warmer to the cooler object, or does it go from the cooler object into the warmer object? Okay. So think about that ice cube example. You're holding ice in your hand. Your hand begins as something that's much warmer, has a higher temperature than the ice cube. The ice cube melts. So using that analogy, then we know that thermal energy flows from the warmer to the cooler object. That's an important law of thermodynamics, which we'll name later. Okay, but thermal energy always flows from the warmer object to the cooler object. And the last thing here to know is that a poor conductor, something that does not allow energy to flow, that's a good insulator. So think about your clothing. Okay, your clothing would be an example of a good insulator. So plastics, woods, fabrics. All right, because our good conductors, like metals, they make horrible insulators because they allow the energy to travel through. And that is it.